Welcome back to the future of clean tech. I'm Rittika, and today we are continuing our fascinating conversation with Dr. Sibo Chetry, a leading expert in advanced materials. Dr. Chetry, thank you for joining us.
Yeah, it's a pleasure, Ritika.
So, to kick things off, could you give our listeners a very brief overview of why porosity is a very critical factor in functional materials, and especially when they are operating in such dynamic and real world conditions?
Yeah, so before starting this porosity concept, I really want to also inform you or all our audience who are listening us is this year 2025 chemistry Nobel Prize was given to this field, this beautiful porous material on metal organic frameworks material has been given. And so I'm really honored to talk about really into this topic. Yeah, so let's come to the porosity. Porosity is absolutely fundamental because it's the gateway that controls everything from how molecules move through catalysts to how ion migrates in the batteries or how gas diffuse through this porosity inside the MOF material or porous material. It will define all the dynamics, kinetics, and everything that is going through these materials are being defined by these terms. But there are the critical insight. The porosity isn't static. Under the real world condition, the porous networks are constantly evolving. And metal organic frameworks might lose 30% of its surface area when exposed to humid air. Or also, this is the same situation in battery electrodes where the pore structure could be collapsed after hundreds of charge cycles, like charging, decharging. So what makes this particularly challenging is that the porosity we measure in pristine lab condition often bear little resemblance to what exists during the actual operations. So we have to be very critical about this one. Yeah.
That's indeed a very powerful point, and I understand that advanced characterization tools are now going beyond static imaging to capture this evolution. Can you explain how techniques like in situ X ray tomography or neutron scattering allow us to observe porosity evolution in real time, and what specific challenges arise when applying these two materials like MOFs and under operational stresses?
Yeah. So I mean, the term that we are talking about here, in situ X-ray tomography or the neutron scatterings, I mean, they are very advanced characterization techniques for porosity. Usually, in a lab-based systems, people are using normal gas absorption device, volumetric statics device, where they expose to like a nitrogen or hydrogen or carbon dioxide, argon. This kind of gases are being used. But yeah, so for many and to understand it correctly, there is so the beautiful techniques like X-ray tomography, neutron scattering line in their ability to peer inside the materials while they actually working. With X-ray tomography, we can generate 3D movies of pore evaluation, literally watching how a catalyst pore network changes as reactant flow through at elevated temperature. We can now resolve features down to 50 nanometer while maintaining the temporal resolution of a minute. Neutron scattering as well as it's very powerful because the neutron interact differently with light elements like hydrogen, giving us a unique insight into how gas molecules behave within the porous frameworks. But one point need to be really understand that this neutron scattering methods usually like to have material where rather than hydrogen they interact much better with deuterium. So that's why many studies on neutron scatterings are being done in deuterated system rather than hydrogen. But this can also be done by many other techniques, also using hydrogen or normal systems as well. So for MOF under the operational stress, I think we have observed fascinating breathing behaviors where entire framework, like the lattice parameter, change with presence of different stimuli, like they expand and contract rhythmically. And if we talk about the one of this breathing material, it's called MIL 53, and this kind of material have shown this beautiful features of gate opening and closing, or you can say expand with the different gases like CO2 or in presence of heat, you name it. So yeah, this is the beauty. I mean, however, the challenge are significant. Yeah, mostly like for the moths are notoriously very sensitive. Like if we are using high energy X-rays, can cause framework degradation, which is quite common. Yeah, that might make a mistaken for operational changes, and we had to develop those minimization strategy and the faster detectors, creating a realistic operando conditions while maintaining the geometric constraint of this instrument require ingenious sample environment. Yeah.
Right. It sounds like you're essentially creating a lab within a massive, massive machine. So, following up on that, how do tools like positron annihilation, lifetime spectroscopy, or PALS, or small angle X ray scattering, right? SAXS, helps quantify hierarchical porosity, and what new insights have you gained from using them on material exposed to humidity or corrosive gases, really?
Yeah. So basically, when we talk about hierarchical porosity, that means the material might have two different types of porosity. Like if we talk about porosity, we are talking about the size of the porosity. And it can be small, it can be big. There's a terms called ultramicroporosity, microporosity, mesoporosities, and some material may have some micro and meso. Then this kind of materials are called hierarchical. But sometimes the problems are being created when the material have small pores, less than a microporosity, or when we talk about size, then it should be zero point 0.7 nanometer. If it's less than that size, then some of these techniques which we well known call as like BET or other techniques using nitrogen, they are ineffective because the size of the system of a MOF of porous materials and the size of the probe gas like nitrogens, they are similar. So that's create a constraint or limitation in the diffusion in the spores. And for that reason, sometimes these techniques like PALS, like positron annihilation lifetime spectroscopy, this is very, very advanced techniques and only can be worked in only some particular labs as well. So we are really fortunate enough to have the access to this facility from SGDR with our colleagues like Ahmed, who is working on this systems, and they are working extensively. And we have seen the porosity using these techniques. So if we talk like the hierarchical porosity is like highway system for molecule. You need a different road size for efficient transport. Else, and is this small angle X-ray scatterings are incredibly complementary for mapping this complexity. Let's give us exquisite sensitivity to micropore and defects. That's very important as well. We're using PALS and a small X-ray, a small angle X-ray scatterings. They are really sensitive to the defect as well. By measuring using for the pulse, we are measuring the like positron lifetime, which directly correlate with the pore size from angstrom to nanometer level. That's what I earlier spoke about. This ZAX, like small angle X-ray scattering, reveal also the mesopore structures, architectures, and also how these larger pores are being connected. Like some of the other literatures where they have shown with humidity exposed zeolites or humidity exposed MOFs, or also similarly for one of our material which were showing this flexible expanding and contracting using pulse revealed something unexpected. Yeah, where it was really interesting to see not only just one time opening and closing but two times. And also like pals can also reveal in many morph like or geolite system where we exposed to the water, where the water didn't just fill the pore uniformly. Instead, it creates a localized cluster that effectively block molecular highway while leaving other pathway open. The ZACs shows us that the mesopore connectivity remain intact, explaining why this material retains some functionality even under harsh conditions. Similarly, let's coming to the corrosive gases, we have seen some or in the literatures that selective pore etching certain pore types are preferentially attacked and creating a new transport pathway while destroying others. And this dynamic restructuring can sometimes improve the performance, while challenges are also for assumption about this material degradation. So we have to be very careful how do we work on those techniques. Yeah.
Right. So the idea of selective pore etching is extremely fascinating to me. So when you're working with so much data from these different techniques, how do you reconcile data from multimodal characterization to model porosity changes in functional materials during real condition cycling?
Yeah, this is a very vast topic. I may not be an full excellent knowledge about that, but yeah, I can give it a small hint. Like in multimodal characterization is essential because no single technique tells the complete story. That's why we always connect many different characterization techniques to come up to a proper conclusion. We have also seen in the literature so-called characterizing fingerprinting or combining electron microscopy for local structures, or sometimes Raman for chemical bond changes, infrared for surface chemistry evaluation for so if we take an example for battery electrodes, we have seen that tracking the porosity changes across charge discharge cycle by correlating electron microscopy image shows the pore morphology with Raman spectra, revealing the stress-induced bond changes in the literature, which was really beautiful. And this can be this would have been not possible if we have not seen many characterization techniques that are being combined together. Similarly, if we see that the key is the temporal synchronization, we need to measure all techniques at relevant states of charge and the environment condition. And we use also like many of the researchers nowadays using the machine learning algorithm to identify patterns across this disparate data set. For instance, many researchers have discovered that certain Raman peak shift consistently preceded major pore structure change visible in electron microscopy, giving that the predictive capability of this material failure. The challenges is that each technique has different sample volume and the time scale. So developing thus may correlate this kind of algorithm that account for this difference. But this is not actually 100% what we are can be achieved right now. So there's still some room for improvement, and many researchers are working on it. Yeah.
That brings up another very important point. When using operando techniques like synchrotron based XAS to track porosity, how do you manage the nuances of not altering the samples, but how do artifacts from beam damage factor into your interpretations really?
Yeah, that's a very beautiful question. Prendo or in Prendo XAS, X-ray adsorption spectroscopy, incredibly powerful for tracking electronic and structural change in real time, but it is also a delicate balance. In high pressure, like suppose in like example, like in high pressure hydrogen environment or acidic electrolytes in battery research, we really need to specialize in cells that maintain the chemical compatibility while allowing X-ray absorption. We have seen also in many literatures that um, we have also seen in literatures that many have researchers have developed a diamond anvil cells with sapphire window for extreme pressure work and the, like polymer line cell for corrosive environment. And also, it is also very well known that beam damage in many constant nemesis, and that's why the many researchers have made a several strategy where they talk about those fractions where they have split measurement across the multiple sample spot, ionic cooling to slow damage kinetics, most importantly damage sensitive control where they have continuously monitor for artifacts. One fascinating, I think, the studies was that controlled beam damage can sometimes reveal hidden information. Like talking about the hydrogen storage, or we are talking about mostly about battery. So let's maybe take the hydrogen storage material. Mild beam damage create point defects, and that become preferentially hydrogen binding sites, mimicking a real operational defects. And this is very interesting because as compared to the normal sites, these defect sites always have unresidual energies and they will preferably absorb hydrogen compared to other. So we have learned to distinguish between harmful artifacts and useful damage that reveal the structure property relationship. The key is establishing damage threshold for each material system and staying well below them while maximizing the signal quality. But this is always hard for porous material like MOF, COF, because for the sample preparation in operando XAS systems sometimes need a harsh techniques like ball millings and all, which break the or degrades the MOF material. So one have to take a extra attention on that. Yeah, apart from that, I think this is a very beautiful techniques and I love it. I tried it during my studies as well.
Indeed, that was a very well rounded answer. So, coming into the fact that the ability to turn a nemesis into a tool is a very big testament to the innovation in this field, actually. Looking ahead, how might AI driven analysis of porosity data from tools like 4D STEM accelerate discoveries in sustainable energy applications, let's say CO2 capture materials, so to say?
Yeah, thank you for the question. I have heard about these techniques. Like, personally, I never use it, but I did studied about them in some paper where the 4D stem generate a massive sets where a researcher can collect a different diffraction patterns from thousands of points across a sample while scanning. Traditional analysis could take months, but AI can identify patterns in real time during the data collections. For CO2 capture materials, many researchers using convolution neural network trained for crystallographic data base to automatically identify local phase and orientation. This has revealed that the effective CO2 sorbent often have subtle structural heterogeneity, not defects. Could be defects sometime, but beneficially local variation in pore geometry that create a preferential binding site. And I have seen the many have developed predictive model that can suggest the optimal synthetic conditions based on desire pore architects or how to formulate like the Nobel laureate like Professor Yagi always talk about this chat GPT trained morph synthesis for desired applications. So I think by training such models on thousands of synthetic structure relationship, the AI can propose a new morph, COF, catalyst, precursors that combine all the thermal treatment schedule that could take years to discover through traditional approach. And this also been also said by Professor Yagi that they have developed the same material with less, which was showing the less porosity, where with using the AI, they have increased their surface and with I don't know tenfold with the CO2 uptake as well. So I think the real breakthrough is autonomous feedback loop, AI analyzing, characterizing data in real time and using like high throughput methods during the synthesis and automatically adjusting the condition to optimize which will directly correlate the pore structures sites different binding sites orientations and it is essentially creating a self-optimizing material synthesis. So yeah, this could be revolutionized in near future.
Right. So, a truly self optimizing system sounds very, very revolutionary. And finally, Dr. Chetri, how do these advanced tools inform the design of robust, porous materials for industrial use? And what interdisciplinary collaborations are needed to bridge the gap between lab scale insights and real world applications?
Yeah, if we talk about lab skills inside to a real world application, the gap between lab scale inside and industrial reality is enormous. But there are many companies nowadays are the key players who are synthesizing MOFs and selling. It's like Promethean from UK, or like there's a very big company, Newmet in US, Florida, by Professor Faha. Some also the BSF have started. Very well known Savanta have started the MOF like ALF-20 for flue gas separations. So yeah, this is interesting how this material, this fascinating materials are being growing and where they are not only just stick to the lab skill but also transformed into industrially. And this could be possible due to the various and advanced characterizations reveal that material behave completely or suitable under these industrial conditions, like higher temperature or different gas streams, or maybe mechanical vibrations and cycling stress that were rarely replicated in the academic or lab settings. And many have established the collaborations with chemical engineers who understood the process. Yeah, many of them also know this techno analysis, what they are really needed for the industrial setups. And yeah, so who model this stress in very different conditions, like they put it into this reactors where they like call it fixed bed reactors or something. And also very important economists who quantify the true cost of the materials replacements cycles, and this has fundamentally changed how we design the experiment. So for example, some of the robust MOF for industrial CO2 capture require understanding not just the chemistry but how material behave in the 30-meter tall towers, columns towers with different temperature gradients and the flow induced vibrations. So or like in flue gas, using people are using this very basic technique called pressure swing methods, and in that they were replicating it. And many have tested this material under simulated industrial conditions from day one, and the most valuable part are the collaborations are the industrial partners. As I told you, the Savante for this ALF-20, they have scaled this up materials. Who provided? So these are the key players who provided the real samples for the process and analyzing this spent MOFs or COFs or catalysts, or yeah, how they are degrading and in a membrane form or in the pellets forms from the actual which teach us how often they can fail and where they can fail, and from where we can learn and then improve in our industrial settings, or also to control in the lab studies. And this have made the discovery that many academic characterization methods miss the most important degradation path, which can only be seen when we collaborate with the big industrial partners. And yeah, because of that, so this can make a really fruitful synergistics between academic and industrial, and can be fruitful for near future for gaining this net zero carbon emission in our environment for sustainable resources.
Thank you so much, Dr. Chetri, for this very rigorous explanation. Listeners, join us next for more.